Hi everybody, and welcome back to Digital VLSI Design. I'm Professor Adam Teman of the EnICS Labs at Bar-Ilan University, and today we'll be going over the Kahoot for Lecture 10, I/O and Pad Ring. Today's Kahoot will have 11 questions, and the first one is, what is the path from a logic gate on the chip to a different chip? Is it gate, I/O circuit, bond bump, package, board, other chip? Gate, bond bump, package, I/O circuit, board, other chip? Gate, board, package, bond bump, I/O circuit, other chip? Or gate, package, I/O circuit, board, bond bump, other chip? Let's see. I guess it would be this one. So let's go and see why. How do we get outside the chip? It's actually a pretty long road from the I/O circuits through bonding through package to board. Once we get out of the chip, we have long wires, which means a lot of delay, capacitance, inductance, but we can use fat wires to have low resistance, and we have a lot more room to play around. Okay, so the package is actually the interface between the IC and the rest of the world. So this is the IC. We have our logic gate. We go through a pad, which takes us to a bond wire. The bond wire goes onto the package, and then the package is connected to the PCB itself. Okay, so we can look at this. This would be our chip. Our chip has some sort of a pad or an I/O connected to a pad, and the pad is connected to a wire like that. These are the bonds. They're connected to the package. This is already part of the package. This will go down onto the board, and we'll solder that onto the board, and then it can be routed to another chip. So we can see that our correct answer was from a logic gate through an I/O circuit, through a bond or a bump, to a package, to the board, and finally arriving at another chip. Question 2. What are the most important requirements of a package? Having a large number of low capacitive wire bonds, being able to remove heat, costing as little possible, or maybe it's all of the above. So let's go back and see why. So the main properties of the package are it provides a physical, temperature, and electrical protection for the chip. It provides electrical connection from the chip to the board, physical connection from the chip to the board, protection from high voltages that come from the outside, physical protection, and thermal isolation for the chip. Okay, so the requirements, therefore, they're the electrical requirements, which means that we should have, low capacitance, low resistance, low inductance, tuned impedance. We should have a large number of I/O pins. That's the interface. The larger the number of I/O pins, the better. It should provide mechanical, protection. So it should protect the die and the bond. It should be compatible with the PCB and be able to connect well to it. It should provide thermal protection, so it should allow heat removal. And of course, it should cost as low as possible, so we don't have to add a fan or a heat sink, etc. So going back to our answers, having a large number of low capacitive wire bonds, so that is two things. We want to have a large number of connections, and we want them to have as low of capacitance as possible. It has to be able to remove heat. That's maybe the most important actually feature of the package, and it's one of the things that makes some packages more expensive than others, is what its heat removal capabilities are, and costing as little as possible. So of course the cost of the package is going to bring up the cost of the chip, so we want it to cost as little as possible. Question 3. Put the package types in order from simplest cheapest to most complex expensive. Is the order BGA QFP PGA dip, dip QFP PGA BGA, QFP dip BGA PGA, dip PGA BGA QFP? Well, I think it's going to be dip QFP PGA and then BGA. So let's just go over that again to remember what these different types are. There are many types of packages. Actually, if you go into Harris's book, CMOS VLSI Design, you'll see there's a long list and a nice picture of different types. But just to get some of the basic ideas, I gave these 4 here in the lecture. So this is the oldest type. this DIP package, the dual inline package. So we have, you know, these pins that go down. They have to go through a hole in the board and be soldered on the other side. And there are very few of them because they're only on two sides. They're dual inline. They're inline and there's two sides. So we have very few bonds actually over here. If the chip is inside, it's a little thing like that, and it's connected with these kind of long wires to it. But that's really the cheapest type of package, and that's how we'll find kind of like discrete components and so forth till today. When we want to get something a bit better, we'll take something like a quad flat package. So quad means that it has pins on all four sides, and since it's flat, it doesn't actually have to go through holes on the board. We just put it on the board and then solder these little pins all over the place. But we can get a lot of these pins on, and we can get a nice pad out from this type of a package. But it's still a pretty cheap package. Okay, then we have a more expensive package would be a PGA, a pin grid array. So here we're going to have several levels of the pins. So you see that there's more than one line of pins. We have three here. They're kind of like staggered, and we'll have some routing inside the package that will actually be able to go and connect to each of the pins without shorting the other ones. Okay, so what we're going to do is we're going to punch holes in, drill holes in the board that are going to be exactly opposite to each one of these pins, and then we can just stick the package. We'll flip it over and stick it inside the board, and then solder the pins from the other side. And the most expensive type of package is a ball grid array, a BGA. So it's the same idea as the PGA in terms of the number of pins that you can see here, because we have several lines of these pins. So we get a lot more pins than, for example, a QFP. But we use these balls, which are like these little pieces of solder here that are stuck on the package, and we have landings on the other side on the board. So we can actually take this thing, just fit it so each of these little balls fits on its relevant position on the board, and then we just heat it up and everything is connected at once. And that makes these very short connections, first of all, many of these connections, and the process of attaching the package to the board is very quick. It's in one shot. So that's the most expensive, and that's the type of package we'll have on all our high-end projects. So DIP, QFP, PGA, and BGA was the right answer. Question number 4. What is not an advantage of flip chip over wire bonding? Pin count, parasitics, RLNC, cost, or fast processing? Well, it must be cost. So there are two main types of packages. Are the old standard type, which is the cheaper one, which is wire bonding. And as we saw here, what we have is we have a die, and we have these pads on the die, which are these areas where we can actually connect something, you know, from the outside world to the VLSI world. And we'll solder a wire, usually a gold wire, onto the pad, and then kind of like a sewing machine, will actually sew this wire over to the other side to land on the package, and we'll solder it again. And the package already has larger legs that can go, and we can solder them onto the board. So that's called a wire bond. Okay. On the other hand, we have the flip chip, and the flip chip is similar to the BGA package. So what we do is we have our on the chip, we'll have openings similar to the pads that we have in the wire bonding, just a bit smaller, and we'll put we'll again put some solder on it. These are called bumps. Okay, and we'll put all these bumps. We can put them all over the package, all over the chip itself. And these touch the die, and then we flip it over, and on the chip has, on the substrate of the chip, we have this array of the landings that the solder bumps fall right onto. So we just heat it up, and then they'll basically the solder will melt and connect to the pads over here. And so again, what we get is a one-shot type of thing, whereas here we have to go for each one of these wire bonds, we have to go and sew it from the die to the package, and it takes some time to do, you know, a few hundred pins or whatever we'd have on the package over here. In this case, it'll be in one shot we get it connected. The other thing is here we can have all of these solder bumps in the middle of the chip. So we have basically, you know, N by N instead of just 4N or whatever kind connections. So we have a lot more connections to the outside world. So flip chip has a lot of advantages over wire bonding. So first of all, as I said, it's this parallel type of bonding process. It happens real fast. Second of all, instead of having this long wire, which has a nice big RLC, so you can see it has like 5 nanohenry and 1 picofarad per wire, we get these really short connections which have 0.1 nanohenry or so. We can get a much larger pin out, pin count with the flip chip over the wire bond. The problem is that it's really expensive. Okay. One of the big things that is also really nice about flip chip is that you can actually put your power and ground into the middle of the chip. So instead of having your IR drop, which will start from the side of the chip and have to kind of route all the way to the middle, and you get some IR drop on the power and ground, you can actually connect your big nice package or board level connection with a strong with a low IR drop to the middle of the chip, and then it just goes straight down and feeds the power grid right underneath instead of having to route from the side. So going back to the Kahoot, pin count is for sure not an advantage of is an advantage of flip chip over wire bonding, as are the parasitics and the fast processing. But cost, the flip chip costs much more. Just designing the flip chip can cost a lot of money, and each of the packages is very expensive as well. Question number 5. What is a pad? So I think I've answered this in the last few minutes, but is it a ball of solder on the chip, a big piece of metal in the top layer, a huge buffer with a very high drive, or a thick layer of plastic that protects the bonded package connections? And obviously it's a big piece of metal in the top layer. So let's see how we interface to the package. And again, we can start with the flip chip over here. So this is the chip itself, and this is in the VLSI process. So usually we have a top metal layer, which is going to be exposed to the outside world. In fact, we usually cover the chip with something called passivation, which protects it from the outside world. But we'll put in the layout these passivation cuts, which will actually expose the metal layer under here. And just because we're going to go wire bond, which means we're going to take this soldering needle kind of thing and land down on it and solder the wire bond to the pad, just for the mechanical strength over there and to lower the resistance. It's not just going to be in one metal layer. It's probably going to be like 4 or so metal layers with arrays of vias underneath. So just in case you break this very thin metal layer, then it won't cause some sort of open or something else, or a short inside the chip. It'll have some protection over there. So these are the pads on a wire bond chip, and here the machine will connect them from one of these pads out to the package itself, which has a much larger pads, which we can really deal with normal machinery or even manually. Okay, but they're pretty big, so they're about 100 by 100 micron. They can be smaller, but that's the kind of order of magnitude of the pitch. The smaller they get, the more expensive it'll be, and the more problems you have, constraints on how what the different angles you can do with the wire bonding and stuff. And these are different types of DRCs that you will get actually from the package house, and you'll have to check. Okay, so that's what a pad is. For a flip chip, again, what we have is we take the top metal, and again we expose the top metal to the outside world, and then with this exposed top metal, we put this solder bump on it, and you have all kinds of layers that help you manufacture this solder bump, so it causes this short circuit to the actual back end layer inside. What is usually used is something we call a redistribution layer, an RDL, and it's an aluminum type of a layer on top of the regular copper layers, which is only used for routing to these bumps. So as you see in this small chip, we have 4x4 bumps on top of, or pad openings, I would call them, on top of the chip, and we have this routing layer, which is this aluminum routing layer, which takes them to whatever IO they should have been connected to, or it can connect straight down to the power grid. And again, we put this passivation opening on top of this top metal, this RDL layer, and then afterwards the package house will connect these solder bumps for you. So you'll get this thing with an array of 16 solder bumps on it, which you then flip, and you'll have an array of 16 landing areas on the package itself, and we'll heat it up and it will connect. So what is a pad? Is it a ball of solder on the chip? No, that's what we call a bump, right? Is it a big piece of metal in a top layer? Yeah, that's what it is exactly. Is it a huge buffer with very high drive? No, that's what we would have as an I/O circuit. And is it a thick layer of plastic that protects the bonded package connections? No, that's the passivation. Question number 6, what kind of circuit is shown in the picture? So here we have a picture of some sort of a circuit over here with, some buffer over here and a buffer over here and a bunch of ports over here and some pull up and pull down, some ESD, some pad in, maybe a resistor, some VDDs. What is it? Is it a digital I/O buffer, an analog I/O buffer, a digital or core power supply I/O, or a pad ring power supply I/O? Well, that's obviously a digital I/O buffer. So going back to where we saw this, a digital I/O buffer is, as it says here, it's an I/O buffer. It provides both input and output. So this is kind of an easy schematic of looking at it. What we have is the output buffer over here, which drives the pad, which is actually the connection that to the pad that we saw before. This is the external part of the chip. This is internal of the chip. So we'll have this part that drives out of the chip, and we'll actually connect this as well to the gate of a buffer that drives into the chip. Okay, and so what we would have over here is an output enable on this guy. So when output is enabled, then this is a driver, and it's going to be driving the pad, and this is configured to be an output. At the same time, we're also going to be tapping this thing, but it goes into a capacitive input, so it doesn't bother us that we're actually driving this out. But if we want this to be an input, and therefore the drive is coming from outside the chip, we disable the output enable, and this becomes high Z. And then if it's high Z, then we can actually drive in things from the external world. So this becomes an I/O buffer. It can be configured to be either an input or an output, and depending on the mode of the chip, usually we'll set a register which will drive this output enable to be a 1 or a 0, and then make this into an output or an input. We also have 4 voltages usually in this guy. We'll have our digital VDD and our core VDD, the VDD that we use inside the chip for the logic gates, and core VSS as well, which is going to usually be 0 volts. Okay, and then we'll have an I/O VDD, which is going to be usually a bit higher voltage. So it used to be something like 5 volts, went down to 3.3, 2.5, 1.8. Nowadays, it could be maybe around 1.2 volts, and a VSS I/O, which is also going to be ground. Sometimes these two guys are shorted. Why do we have 2 different voltages over here? Well, mainly because the I/Os, they're going to be, when we drive an output bus, it's going to need a lot of current to go into the large capacitance we have outside the chip. So the need to drive that current is going to cause voltage, a lot of current pull from the VDD, and that could impede the level of the VDD that's going inside the chip. So that's why we separate them. So when we are driving some sort of an output bus or something like that outside the chip, it will only affect the VDD I/O, and it shouldn't affect the VDD, which is a completely separate voltage. That's number 1, and that's why we have the separation between the VSS and VSS I/O. I guess the VDD and VDD I/O are usually going to be on different voltages as well. So of course these buffers are also going to be level shifters. So this is going to be an upshifter, and this is going to be a downshifter. Okay. The other things that are shown in this picture that I showed you up top here are going to be the ESD protection, which we're going to discuss in a moment in one of the next questions. We're going to have a resistor here as well for the ESD protection, and we're going to have pull up and pull down capabilities, where if we're not actually using this I/O, if it's not connected, if it's not driving anything, it's going to be either pulled up or pulled down to a 1 or to a 0. So we won't have any floating nodes on the board, which may then drive some sort of intermediate, something in between 0 and 1 somewhere else. But they're going to be really weak pull up or pull down. So once you want to overdrive them, it's not going to be a problem. So that's what a digital I/O buffer looks like. just for a reminder, analog I/O buffer is basically just a wire. Okay, it's going to be a wire. It's going to be ESD protected, but it's just going to be a wire, so it allows us to have, some levels in between 0 or 1, where the digital I/O buffers will only be 0 or 1 with a level shifter inside. Core power supplies and I/O power supplies are just going to be those supplies that actually tap the rings and provide the voltage from the outside to the inside. But they're actually a type of a analog I/O buffer, you could say. Okay, question 7. What is illustrated in the following picture? So what is this? Is it electromigration protection? Is it antenna protection diodes? Is it impedance matching for 50 ohms? Or is it electrostatic discharge protection? Well, I mentioned it before, and it's pretty obvious that this is electrostatic discharge, or ESD protection. So let's go over what that means, because it's pretty essential and important. So one of the most important reliability problems in the IC industry is ESD. So what happens is, when you get something in the outside world, such as a human being, we have a whole bunch of charge that's stored on us, and that charge is looking for a way to discharge to ground. And if we touch the the chip, then if we touch the pad, then it can go and hit one of these CMOS gates, which are very, very thin, and burn it out. And that's really bad, because that will burn out our chip. So first of all, when you're working with chips in the lab, always, ground yourself and work in an ESD, in a protection type of environment. But also, we need to put these ESD protections on all of the inputs and outputs, mainly inputs to our chip. Okay, so how is it done? It's done with these diode clamps. So we have a couple of diodes, and you see they're connected in the same direction. And so we have the pad over here, which say it's going to get hit with a big, a big spike of voltage. Okay, so if we have these diodes over here, and the top one is going to be connected over here to VDD, the bottom one is going to be connected to ground. And since the level over here in general is going to be between VDD and ground, both of these diodes are in reverse bias, and they don't do anything. But if we have a really, really high voltage spike, so this goes up to like whatever, 1,000 volts or something like that, this diode's going to turn on, and it's going to, instead of the current and the voltage going in, burning out the gates over here, it's going to discharge that through the diode. The same thing happens if we have this highly negative voltage. It's going to turn on this guy, and it's going to discharge the current and protect the CMOS gate that's inside, the buffer that's inside, or whatever we have inside the chip. We also have a current limiting resistor, so it won't happen immediately. When the current that tries to pass this voltage goes through there, it's going to really take the voltage on top of it. So it's going to be not a huge resistor, but resistor that can limit the current that actually goes and flows in through the pad over here. Okay, usually we do this in 2 stages. We have the primary ESD elements, which are going to be the real big ones, and they're going to provide the protection. But we're also going to have a little pair of these diodes that are going to be after the current limiting resistor. So they will do this protection that's close to the internal circuits until these guys kick in and start working. So that's ESD protection. The rest of the things were just electromigration protection, of course, is actually by using copper wires and by making them wide enough. Antenna protection diodes are a certain standard cell we have in the library, where we're going to put them near a gate when we see that we have an antenna problem to protect the gate. And impedance matching is something that we do want to do. We want to have a 50 ohm impedance looking in from the outside world to eliminate reflections, but that's not what this circuit is. Question 8. How do we supply ESD protection voltages to digital I/O buffers? We connect them with analog I/Os, plain wires. The power supply cells connect to the I/O rings. We add capacitors to the package pins. We connect these voltages through the chip's power grid. What are we going to do? The power supply cells connect to the I/O rings, of course. So let's see that. So this is a picture that I showed inside. So this is our ESD protection. We have our pad from the outside world, we have our signal that's going to come in, and again, it's going to be between VSS and VDD, right? And we have our diodes over here. So the diodes, the other sides are going to be connected to usually to VSS IO and to VDD IO. And that's to provide the protection. So where are these VDD IO and VSS IO coming from? That's the big question. Well, what we do is we have a ring around the entire chip. So we're going to put our IOs in the periphery of the chip, at least traditionally in wire bonding, okay? And we're going to have 4 rings running around the entire periphery of the chip. One of them is going to be VSS core, one of them is going to be VDD core, one of them is going to be VSS IO, and one of them is going to be VDD IO. And then if we just instantiate some sort of IO cell over here, like a digital IO buffer, it can easily connect the diodes that it has inside to these voltages. It just has them there so it can tap to them. Then we need, the cells that provide these voltages. So we'll have pads that actually are, what they do is they take the VDD voltage from the outside world and connect it to the VDD rail. They take the VDD IO from the outside world and connect it to the VDD IO rail, etc. And actually, the number of these pads that we have to put there has to be, sufficient to provide the voltages, the voltages and the current well enough to the chip. Okay, so those are the power supply IOs that we have. So what we're going to have is we're going to have at least 4 power supply IOs, and we're probably going to have something like at least 1 on each side of the chip, probably many on each side of the chip. When we go over to flip chip, it's not exactly the same thing. So we do need these rails these rings in order to provide the ESD protection even in the flip chip. But we can stick our IOs in the middle of the chip. We can make a little line of IOs. But since we need to provide, the 4 power supply IOs for that area, we need to have a sufficient number of IOs in order to really utilize the fact that we would have our IOs sitting in the middle of the chip. So even in flip chips, we usually do put all the IOs around the periphery and only have power connections, which we want to, really come into the middle of the chip. We'll have them in the middle. Maybe we can have some secondary, type of IO areas, but it's not usually the case. Usually, even on the flip chips, we have this IO ring around. So the question was, how do we supply the ESD protection? And the answer, of course, was that the power supply cells connect to the IO rings, which we showed above. I wrote that we could connect them with analog IOs, but analog IOs actually don't connect at all in some cases to the ESD. So just going back over here, if we put an analog IO over here, it will also probably have these diodes to protect it. But that is in case we want an analog IO that has an analog voltage between VSS and VDD. What if we want a higher voltage or a lower voltage going through the analog IO? Then we cannot actually connect them to these. So you'll have cases where you'll do that. You'll have analog IOs that will not have ESD protection. And what you should do is add one of these clamps. Usually there's going to be an IO clamp in the library to connect it to at least the voltage that you're not going to pass, or to protect it with the highest or lowest voltage you're going to ever reach. We can add capacitors to the package pins. That's not going to provide us with ESD protection in that way. And we can connect these voltages through the chip's power grid. And again, that's not what we do. We do connect the power grid to the power supply cells are going to connect to the power grid, but that's not for the ESD protection. Question 9. Mark the order of the pad configuration approaches from worst to best in terms of area pinout efficiency. Flip chip, inline, CUP, staggered, inline, CUP, staggered, flip chip, CUP, flip chip, inline, staggered, or inline, staggered, CUP, flip chip. I think this is going to be it. So let's go and take a look at that. So our first pad configuration is the standard inline pad configuration. You see here we have these are IO circuits. They're going to be right next to each other, and each one of them is connected to a bond pad, which is going to be separate from them. That's the standard, simplest inline linear type of way of making this, but it's really wasteful in terms of area and so forth. The bond pad, which has this quite large pitch, is going to really set the number of pads we can have along the side, and the I/O circuits are going to be one I/O circuit for each bond pad, going to take up a lot of room underneath, and it really eats away from a lot of our chip. But that was the standard way of doing it. At some point they developed this staggered way. So since the bond pads are pretty big in terms of the amount of space they take up, on the width side, and we can make the IOs thinner than them. So what we could do actually is stagger the bond pads over here, so they take up a bit more of the of this direction. But then again, we can have more connections outside our chip. We can raise our pin out in this way, so the actual the area this will take up is larger than the area that would take up, but we get a factor of 2 almost more bond pads, more connections to the outside world. So you can have 3 levels of staggering as well in some libraries. What makes this even more efficient is doing what we call CUP, or circuit under pad. And so circuit under pad, if you can see here, we have the bond pads over here. They go down to something like metal 5 or something like that. So from the top metal down to metal 5, and we implement the IO with the metals under it. So the circuit, the IO itself, is protected because we have these several layers of metal on top of it. So it's still protected, but we can set the bond on top of it, and then we don't waste this area that is just for the bond. The bond comes and is sitting on top of the pad, and it takes up less room, and we can even stagger them, as you can see in this picture. And of course, the most complex and best way to do it is the flip chip using RDL. So here we can really have bumps all over, all over our chip in any place, and we route to them with our RDL layer, our redistribution layer, this special top layer aluminum that can really route just from whatever circuit it wants to connect to the pad over here. So the answer is, of course, inline is the worst, staggered is a bit better, CUP is a bit better than that, and flip chip is the best. Question number 10, what is an SIP? Is it integration of several IPs on a single silicon substrate, integration of several silicon devices, chips, in a single package, integration of several chips on a single PCB, or integration of several PCBs in a single product? So it's going to be this one. So an SIP, we said, is a system in package. So what's the difference between an SoC, which is system on chip, and an SIP, which is system in package? So a system on chip, which is an idea we've been using for several decades now, is when we take several IPs and put them on a single silicon substrate. So instead of just having, each chip performing a single function, since we have a lot of real estate on the chip nowadays, we can put a lot of functionality. We're going to take several of the things like both the core and the and the peripherals and accelerators and so forth, and stick them on one single chip. And that's what's called a system on chip, and that's what almost all of our chips are nowadays. System on package is a more advanced kind of an idea, where we're actually going to take several of these system on chips and put them inside the same package. Okay, and the reason for that is that we can't make the SoCs infinitely large. The larger you make the SoC, the lower your yield is going to go down. So instead of that, we can take smaller chips, which will have high yield, and connect them together with some sort of a special way inside of a package to get to do it better than bonding or flip chip, which we're going to discuss in a second, and we're going to get something better. Plus, we can also mix and match different types of dies, different flavors of process, different nodes of process, and so forth, according to what we need, versus a monolithic type of a die that's going to be made in one process technology with one flavor of the process. So integration of several IPs on a single silicon substrate is an SoC. Integration of several silicon devices in a single package, that's a SIP, a system in package. Integration of several chips on a single PCB, well, that's what we do. We usually take a PCB, printed circuit board, and put several chips on top. So that's just a regular, board. And integration of several PCBs in a single product, that would be a product with multiple PCBs inside, which many of the products are. And finally, our last question. Which of the following technology uses TSVs? TSVs are through silicon vias. Does flip chip use it? Does MCM use it? Does CoWoS use it, or does HPC use it? Well, the answer is going to be CoWoS. So let's go and look at that. So I gave an overview of some of the system in package approaches that exist today. So one of them is MCM. That's a multi-chip module. MCM is pretty. It's not a new idea. It's been around for maybe 20 years or so, maybe even more than that, where we take a single package and we put several chips inside. But you can see that this is wire bonded, right? We have one chip is sitting up here. We can put the other chip on top of it, and we can make these really nice wire bonds just by connecting a pad on this chip to a pad on this chip. So this is going to be a real short bond. It doesn't need to go through the board and so forth to connect the two chips, and then we can put this all into one package. It's a real nice thing. So MCM has been around for a long time. You can also use like a little mini board inside the chip, put two chips next to each other, but in any case, we're going to have real short wire bonds and so forth. That's the multi-chip module. Okay, the next like level of that is what we would call silicon interposers, and TSMC's one of their products that they provide is called CoWoS for doing this. So what you do actually is you have your package substrate, the regular package substrate, just like this one is over down here. But on top of that, you put what we call a silicon interposer. So this is a VLSI chip. This would be in something like 65 nanometer technology or something, and it is not used for creating logic. It's only used for creating interconnect. And we have our different chips, which are going to be in whatever logic we want them, and we'll put them next to each other over here. And we put these through silicon vias. So we have a hole basically through the substrate that's going to be able to go down and connect underneath the chip. And then the interposer also has through silicon vias, but it'll also have routing between, as you can see here, between two of these bonds over here. They're going to be connected in a VLSI layer on the silicon interposer, and another one's going to be connected to the package through silicon via. So each of the times that we actually punch through the substrate of the silicon, that's going to be using a TSV, which is the answer to the question that I asked. Some other things that we have are HBM. That's the high bandwidth memory. That's one of the types of DRAM approaches that has been used for 3D integration. And you can see something like this. So we have one of these silicon interposers similar to what we have over here, right? We'll put our SoC or whatever our main product is going to be on top of it, and it's going to connect to just DRAM through the substrate, through the silicon interposer, to get nice nice and short bonds to it. And then the DRAM is actually going to be stacked in a 3D fashion, and because it's a special type of a way of doing it, we can put lots and lots of DRAM slices on top of each other and get really high bandwidth, a lot of memory in a small area. So HBM is used in things like GPUs and so forth, where we need like really fast and a lot of DRAM. Okay, so that was kind of an earlier generation, I would say, of what we would call 3D integration. This would probably be called 2.5D integration. This is real 3D integration when we have these stacks of DRAM, but it's really been around for several years now, even though it's pretty high-end and expensive, so it's not used across the board. The newer stuff that's come out recently is Intel has a process called Foveros, and TSMC has SOIC, and there are different ones from a couple of different companies that they've showed real 3D integration, where we have some sort of a mixture between, this silicon interposer type of a thing, where we have some dies over here that have through via connections and so forth, but we can actually stack in a 3D fashion chips on top of each other and route using through silicon vias between them. So this is really pretty new. It's not used that much, but it's up and coming, and for sure that's the way that a lot of the future things are going to be made, with chiplets and so forth. Okay, the more futuristic kind of look at things is what we call monolithic 3D, and that's where we're going to actually build chips one on top of the other, and we're going to have through silicon, just extra layers of chips one on top of the other. And there are several works and several companies that are working on this, but some really nice stuff that has been presented in Nature in the last few years from a group at MIT and Stanford has done some of this cool stuff. So when we go back to the answer, MCM does not use through silicon vias. It's just a bunch of chips that are in the same package and they're probably wire bonded together. Flip chip doesn't use through silicon vias. It has its bumps on the top layer. HPC is actually it stands for high performance computing. It doesn't have anything to do with packaging technology. I mean, it uses obviously packaging technology, but not in the context of this question. And CoWoS is TSMC's one of TSMC's products for 2.5D integration, which does use through silicon vias. So that's it for this lecture, and any questions, you're welcome to ask me on my YouTube channel, and I'll be happy to try and answer them.